All right, inorganic chemistry, the next continuing chapter we have at hand is acids, bases, and salt preparations. We have previously learned, as per the pH system and the whole set of indicators, what acids, alkalis, or bases are. We've also learned how acids and alkalis react together in neutralization reaction and produce salts. But in this chapter, we're going to study about salts further and how to produce them from different reactions. So, starting off with the very definition of salt, all acids contain hydrogen. For example, HCl, hydrochloric acid, sulfuric acid, H2SO4, nitric acid, HNO3. If I keep giving examples, I'll keep adding some formulas over here, which would contain the H hydrogen in it. And the definition of salt is pretty simple. When this hydrogen is replaced by a metal, the compound formed is known as a salt. Let's suppose I don't write H over here. Instead, I write sodium. It's now a salt. For example, I don't write this H over here. I write magnesium. It's now a salt. For example, I don't write H over here and I write aluminum. Along with that, I readjust the formula a little bit as per valencies or oxidation states. Now this is aluminum nitrate and this is also a salt. So every time I replace this H with uh, salt, I produce with a metal, I produce a salt. So we have different examples in front of us. The book gives us the example of zinc fluoride, which is ZnCl2, or potassium nitrate, which is KNO3. So by saying these different names, I hope you get familiar with different salts. So there can be so many different salts. Imagine if I just replace this H with start with different elements with Na, with Mg, with Al, with Zn, with Fl, how many different salts can I produce from the same acid? So there are a number of salts around us, and yeah, we use many in our daily life. The most common one is sodium chloride, and we use it as a table salt. And of course, the tables right in front of you also starts with that example. Take a look at this hydrochloric acid. We replace the H, the sodium. We have a chloride salt. Now notice, hydrochloric acid would every time give us a chloride salt. Nitric acid would every time give us a nitrate salt. Sulfuric acid would every time give us a sulfate salt. Ethanoic acid, for which if we take out this H, the rest is ethanoate ion, that every time gives us an ethanoate salt. Phosphoric acid gives us a phosphate salt. So in this way, whichever the acid is, we give it the name of parent acid since it's the parent of the salt we are about to produce. So parent acid gives the specific salt. And the names are pretty similar. Chloric acid, chloride salt, nitric acid, nitrate salt, sulfuric acid, sulfate salt, so on and so forth. So I hope we understand that this kind of naming and what the parent acid and what the child salt would be. A couple of things that the book is about to clear for us. Let's go through these lines. Sulfuric acid can be thought of a parent acid of all the sulfates. The salt formed from sulfuric acids are called sulfates. It doesn't matter, replacement of hydrogen can't be done directly or not. For example, you can't make copper sulfate from copper or dilute sulfuric acid because they do not react. But however, there are other methods of making the same salt, so you need not worry. But copper to sulfate does exist as a salt. So salts are also formed when we replace hydrogen, not with a metal, but with this ion. This is known as an ammonium ion. I'll be exact by placing the positive sign on top of it, which is also given over here. This is known as ammonium ion. Ammonium ion also makes ammonium salt, for example, ammonium chloride, ammonium sulfate, ammonium nitrate, the list would go on. Though this is not a metal, it's not made up of metals either. Both nitrogen and hydrogen are non-metals, but still we call it a salt. And it is a salt from these definitions. So let's consider which reactions of acids we need to understand can produce salt. Now, well, we already know a few. To begin with, we do understand salts can be produced by reacting acids with metals. Simple dilute acids react with metals depending upon their position in reactivity series. Metals below hydrogen in the reactivity series do not react with the dilute acids. Here, we need a little bit of understanding. I hope you understand there were some reactive metals in the reactivity series. I'm not going to go through all of them over here, but even if I name a few out of them, that would be calcium, sodium, magnesium, potassium, lithium. They were on the list. And then we had carbon over here. After carbon, you had zinc, iron, tin, lead, those kind of stuff. But then we have hydrogen, and then we have copper, silver, gold, and like that. So anything below hydrogen, which in this case we have these three, right? They do not react with dilute acids. And by these dilute acids, we typically mean dilute HCl, right? Why? They're less reactive. Hydrogen cannot really replace them. Hydrogen can really replace them. They can't replace hydrogen. My bad. So metals above in the series, they definitely react, and they react with this method. The metal reacts with the acid, it actually replaces the hydrogen, it produces the salt, and hydrogen replaced is given out as hydrogen gas. The higher the metal in the reactivity series, the more vigorous the reaction is going to be. And some of the elements like sodium, potassium, calcium, the reactions are too violent, we don't even perform them in school labs. Now, this is a very generic statement. You can make so many equations out of it. And in order to remember this, we have this mnemonic, MASH. Metal is a salt hydrogen. And it's a very easy mnemonic to remember. Let's quote a few equations related to this specific general idea. For example, if you react, let's say, magnesium with HCl, it's going to give you magnesium chloride, the formula for which is MgCl2, plus it's going to release some hydrogen gas, which is H2. Of course, this equation needs balancing. There you go ahead and balance it. So take a look at this. This is a metal, this is an acid, this is a salt, this is hydrogen gas. This follows the same pattern. Let's change the metal and the acid this time and try to figure out whether they'll have the same equations or not. I'm going to write it over here. So let's replace the metal with zinc. Let's replace the acid with, let's say, this time we have sulfuric acid, right? It's going to produce zinc sulfate, and along with that, it's going to produce hydrogen. How do we produce it? It's pretty easy, by the way. We take the metal, we take the negative part of the acid. That's how we form the salt. It's just the hydrogen that is given out as hydrogen gas. So it's pretty easy to combine this with this. Let's do it again. This time, let's do it differently. Let's say we have iron and we react it with nitric acid and we produce iron nitrate. Thus, it's definitely going to give out hydrogen gas. Let's balance the entire equation. There you go, we have balanced it. Again, metal plus acid gives us salt plus hydrogen. That's how easy it is. But remember, we only give you the idea how it's going to go. Which metal you might need to react, which acid you need to react it with, is something that is usually directed in the paper. And remember, there can be a trick question. Let's consider something like this. Let's erase it first. Okay, copper is going to react with HCl. Let me tell you, no reaction. Why? That's the very first line mentioned over here. Anything below the hydrogen in the reactivity series does not react with dilute acids. So don't fall for the trap. Although most of the other metals on top of hydrogen work in the other way around, they react with acid, they give salt and hydrogen. These, copper, silver, gold, are not going to give these reactions. I hope this makes sense to you. Does it?
Yeah.
Good, good. Practicing a few equations gets the student good with this stuff. However, you still need to remember how mesh works. Okay? So moving on, Reactions involving magnesium and acid, for example, I've already considered this example, but I was talking about a different acid. They have considered sulfuric acid. However, what the book is going to tell you on top of just the equation is also the observation. So let's consider the whole thing, because this time it's not just the reaction we're only concerned with, we're also going to study observation. So you already are familiar with the reaction. The metal reacts with the acid, it produces a salt, it gives us hydrogen, the mesh is completed. But there is rapid fizzing. Fizzing means effervescence or bubbling, and there is a colorless gas involved, which definitely is hydrogen gas. Now, this gas pops with a lighted flint. This is actually a test for hydrogen and a really fun test at lab. I've seen students doing this test again and again because of the pop sound it makes. Usually they are saying it's pop, but usually it's the ta voice we commonly talk about in our language, and it's really fun for students. It's like the small funny explosions they can go with doing in lab, and it's like a dream comes true for many students in terms of explosion. Of course, it's not going to explode the whole lab, and we don't pray for anything like that too. But yeah, it is fun. So students enjoy it. Reaction mixture becomes warm as heat is produced. The magnesium gradually disappears. It leaves us a colorless solution. Why? Because the salt makes a colorless solution. But remember, this is a salt of a normal element. That's why it's a colorless solution. If it were a transition element, it can be a colored solution. So it's up to you to write the observations in the correct manner, since this is something we have already taught you. And you know the normal elements give you colorless solutions, transition elements and their salts give you colored solutions. So, yeah, I hope you understand the fact. This is a displacement reaction. Magnesium, being more reactive, displaced hydrogen, formed the salt, and pushed hydrogen apart as separately as hydrogen gas. So the same thing is mentioned over here. I hope this is understandable for you. Is it?
Yeah.
Good. So this is magnesium reacting with dilute sulfuric acid. This is all the bubbles, the fizzing, the same kind of fizzing or bubbles we see in any carbonated drink, soft drink, cool drink, Coke, Sprite, Fanta, you name it. You might see some bubbles like this. Though the color in those carbonated drinks might interfere with the color of the bubbles, but I hope the observation about the fizzing part is the same. So if I talk about dilute hydrochloric acid, the equation really looks the same to what I wrote previously. Of course, we're going to have the same set of observations. We are going to get a colorless salt solution, a simple white colored salt. We are going to get the fizzing due to the production of the gas. That gas can be tested with a lighted splint. The lighted splint will be extinguished with a pop sound. So everything else is the same. Now, if we talk about these equations to be written as ionic equation, which is actually a part of extension work and which is a very common question in past papers, then let me tell you that all the negative ions in the system in this equation in specific are spectator ions, which means if I take this whole equation, this equation was magnesium as a solid plus sulfuric acid, which I took as an aqueous solution in water, gave us magnesium sulfate, the salt, which is very much soluble in water. So I'm also going to write this as an aqueous solution. Plus, it gave us hydrogen gas, which is insoluble in water, so it bubbles out of the system. Now, I hope you understand we need to write it, the aqueous systems, these and these, as separate ions in ionic equation. So let's rewrite the whole equation. Magnesium is a solid, plus we have two H positive ions in aqueous solution. Why? Because the ions are separated in aqueous solution, thus we have sulfate ions in aqueous solution. It's going to give us the magnesium ions in aqueous solution, so Mg2 positive. It's also going to give us the sulfate ion solutions again on this side. Plus, it's going to give us, my bad, these are two negative, and the hydrogen gas. Now, if you remember the method, after writing the whole equation into ions, we actually cut out the ones which have the exact same formula on both sides, as well as the exact same state symbol. So the sulfate ions with the state symbol aqueous are same on both sides. If I cut that out, what am I left with? I'm left with these two parts and these two parts. So I'm left with this equation exactly.
Mhm.
So instead of writing it over here, you can see it over here, which means negative ion was the spectator ion. If I write that with the hydrochloric acid equation, I find out that again the negative ion is the spectator ion. So it's pretty simple. If I cut this one out and this one out, the rest I'm left with is the ionic equation. That's how simple it is for these displacement equations. I say it is this simple for MASH equations in specific. Remember, ionic compound is present as separate ions in solutions. Why? Because they get separated and they're actually surrounded by water molecules. That's why we can write them separately too. Okay. I hope
Yeah.
this is understandable. We have done this kind of practice before. It was just a repetition. Let's talk about other metals. Let's talk about zinc as a metal. Now, what is book trying to do? Let me clarify. I hope you remember I drew you the reactivity series of reactive metals up top. And then I told you that there is a non-metal in between, which is carbon. And then we have zinc and iron. And then again, we have a non-metal, hydrogen in between. And then we have copper, silver, and gold. Notice from this, the book picked magnesium and gave us all the examples. From these two, the book is going to pick zinc and give us all the examples. And then the book will briefly discuss these. Though these don't react directly with the acid, but still we need to discuss these. So we'll pick an example out of this and discuss this. I hope you understand what is book trying to do. It's trying to bifurcate the whole series into three parts and teach you each part one by one. The first part was taught to you by the example of magnesium. We're going to study the second part, which is a really small portion in reactivity series in your book. And we're going to take zinc as an example out of this part. So moving on with the example of zinc, zinc is going to react in the same way. Since I've mentioned a couple of equations like this already, so there should not be a problem. I hope you understand as soon as you read that when zinc reacts with sulfuric acid, it produces zinc sulfate salt and hydrogen gas. Same happens with hydrochloric acid. The salt is different. It gives you chloride salt, but I was calling it same because of the production of hydrogen as the fizzing observation. Take out the negative ions out of this. If I cut the sulfate and sulfate out of this, or if I get the chloride and chloride out of this, that's what I get. And the same thing is mentioned over here. The ionic equation in both the cases is actually the same. This is a very good point that they have explained. So it really does not matter which acid we are using, as long as we are using the same acid, we get the same ionic equation. So it's pretty simple. Whichever acid it is, the ionic equation will be the same. Now, that was the first kind of reaction. Metals reacting with acid producing salt. That's what the first kind of reaction was. Now, what if the acid does not need to react with the metal? It can react with something else and can still produce the salt. Let's talk about that. For that, the book has started off with basis definition. So we understand anything that can neutralize acid by combining with the hydrogen ions and using them to produce something neutral like water is considered as a base. The base can be a metal oxide, it can be a metal hydroxide, it can also be ammonia. So when acids react with bases, the good part is that they produce salt and water. So if you react dilute sulfuric acid with copper oxide, that's what going that is what going to happen. A metal oxide is actually a base, so acid, salt, and water. That is also given as BASW, base acid salt water. Sometimes it's also given as ABSW, means the same thing. You can use the mnemonic to remember it. Remember, metal oxides are usually bases.
Mhm.
So, taking a specific example of copper oxide, which is a black powder, it reacts with hot dilute sulfuric acid, produces a blue solution of copper sulfate. Now, as soon as you see a transition element, you see the solutions are not colorless anymore. It's a blue solution. So that's the best part about transition elements. You know that most of their salt solutions are going to end up as colored salts and not colorless. Okay. So it is going to produce water. And you see the same thing. So it's a base, it's an acid, it produces a salt, it gives us water. The same mnemonic. All the metal oxides and acid combinations you will see here react in the same way. They produce a salt and water. Sometimes need the heat for the reaction to start. Uh, Cu2O, oh, sorry, CuO or copper 2 oxide is actually an ionic compound. It contains this oxide ion, which can react with hydrogen ions and they can produce water. So if I talk about these base reactions in specific, I can safely say that these reactions give this kind of ionic equation. O negative 2 plus 2H positive gives us H2O, that is solid, plus aqueous gives us a liquid. Again, this is the ionic equation for this one, which is not mentioned over here. Remember, this is a neutralization reaction because the base neutralizes the acid or vice versa, forming water. You might need to write this equation down, but you can find it later in a part of book or in past papers as well. Okay,
Yeah.
moving on. Bases and alkalis. Now we know all alkalis are bases. Alkalis, we call them as alkalis. Why? Because they are those bases which can dissolve in water. So it's pretty simple. Water soluble bases are known as alkalis. Some metal oxides are soluble in water. They sometimes react with water and they produce hydroxides, which are then commonly known as alkalis. So this oxide can dissolve or react with water to produce an alkali. All group 1 oxides do the same reaction, they produce alkali. Most other metal oxides are not soluble in water, except for a couple of them from group 2, for example, calcium oxide. This slightly dissolves in water to form calcium hydroxide. Another alkali that we will meet that can react with water and produce the hydroxide ion is ammonia. That's why we call ammonia as a part of base. Why? Because they can neutralize acid, or when they dissolve in water, they produce alkalis. Then this whole formula becomes NH4OH. Keep that in mind. It can be written separately or together as an aqueous compound. It's up to you. We sometimes also write this as NH3 aqueous. It's up to you which way you would like to write it. Both the ways it's acceptable and gets you complete marks. So reacting acids with metal hydroxides. Now, metal hydroxides are actually alkalis. So this is A plus A giving us S plus W. So this was BASW and this is then AASW. So that one is base acid, salt and water. This one is alkali acid, salt and water. Metal hydroxide is the alkali and metal oxide was the base. That's an easier way to bifurcate between them. Let's take an example out of metal hydroxide. So dilute hydrochloric acid, and this time the hydroxide example is sodium hydroxide. So if you mix these two solutions, they produce a colorless solution. Not much seems to have happened, but if you repeat the reaction with the thermometer, you can see the temperature rises several degrees. That makes sure that it is a chemical change. Neutralization sometimes comes with heat. That's why. This is also a neutralization reaction. An alkali reacts with acid. neutralizes the H positive ions to form the neutral water. And this is going to be the exact specific equation, ionic equation from it. Why H positive ions are always given out from acids, OH negative ions are always given out of alkalis, and they form the neutral water. Hence the name of the reaction, neutralization, which brings us to another kind of reaction. Now, that is the third kind of reaction that produces, actually four, if I count all of the order of your book, the fourth kind of reaction that produces a salt for us. How acids can react with carbonate salt. And this time the reaction would be a little bit different. The carbonate salt, when it reacts with acid, it produces salt and water, but along with that, it produces carbon dioxide. This is another good example. This is CaSA, sorry, SCW. Carbonate, acid, salt, carbon dioxide, water. Sometimes it's also CaSCOW, Cascow, but it's really up to you which mnemonic you like, or can you do it without a mnemonic? It's totally up to you. So if I go with this example again with a proper names. So copper to carbonate and dilute acid can be used, different dilute acids. We form different salts, but the rest of the product the same, notice. Now copper to carbonate, as soon as reacts with acids, this gives us most of the salts that are blue. Copper sulfate is blue, copper nitrate is blue. So carbon dioxide gas is given off. We can recognize it because carbon dioxide can turn lime water milky. That's another test to prove it's carbon dioxide gas. It converts the clear lime water solution into a milky one. This blue depicts a copper salt. Of course, the transition element can show us a colored solution. So if we work this one out, this one has also a specific equation. This is the equation. Carbonate, when reacts with hydrogen ions, gives us carbon dioxide and water. All the ions in the salt, sodium, chloride, chloride, sodium, are actually the spectator ions. So the equation is all about acid reacting with carbonate and producing carbon dioxide and water. Okay. Carbonates are not mentioned as bases on the syllabus. Base also only contains metal oxides, metal hydroxides, and ammonia. Carbonate is something different. So this is considered a separate category, not a category under base. This completes our first half of the chapter. So making a quick mind map out of it would be a great idea. So we have some space over here. Let's do it over here. So there are a total of four reactions. One, two, three, four that I'm going to use, and all four of them are going to give us salt. First one was base plus acid that gave us salt plus water, or I can use metal plus acid that can give us salt plus hydrogen, or alkali plus acid that can give us the same product as number one, salt plus water, or I can finally go with carbonate plus acid that can give us salt plus water, plus it gave us carbon dioxide. You can write carbon dioxide up top and water after, it's up to you. So in all these cases, you notice we're producing salt in every case as a product and acid in every case as a reactant. And you'd notice that again, the production of salt depends upon the negative ion of the acid. Every time the salt we produce would be something that would have a parent acid. So if the acid is sulfuric acid, the salt would be sulfate salt. If the acid is hydrochloric acid, no matter which kind of reaction I'm going with, the salt will always be a chloride salt. If the acid is nitric acid, the salt would be a nitrate salt. That's how easy it is for you to remember. So that's the
All right.
whole mind map of the four type of reactions we are done with today. Any questions?